Hi everybody, today we are going to talk about task 2 for embedded system designs. In this task with the name of task embedded system hardware. In this task we are going to talk about embedded system interface, DC motor speed and direction control, stepper motor control. So first of all, as you all know, the microcontrollers are different families. Here we have the ATmega8. ATmega8 contains 28 pins, in which we have ports D, B, C. Okay, 3 ports are available here. Each port has 8 bits, so it has 28 bits, 28 pins, which are mostly used for input output. So how do we configure this? So the hardware of the ATmega8, as you can see here, it has 32 by 8 register file. It has input-output modules, which we control through them the input-output. It has an ALU, which is an arithmetic and logic unit controlling all the operations. And it has an EEPROM flash storage memory. EEPROM stands for erasable, electrically erasable, programmable read-only memory, which is the size of 8 kilobytes in size and 16 bit words. This is bit words. Okay, so as you can see here, this is the microcontroller. This is the input output port. As you know earlier from task 1, we know that from microprocessors and microcontroller course, we know that to control any port we need DDRX, port X, PNX. These 3 control any port. You can see here this shape is a tri-state buffer, where this is an enable for the tri-state buffer, and this is the actual physical pin over here. Now, in order to control a DC motor, of course the implementation and code for this will be explained later in the programs. So it's quite straightforward, and it was already explained for you in the microprocessor and microcontroller course Comp 3300. Now, controlling a DC motor. In order to control a DC motor, we need to control its speed and its direction. Now, the direction depends on the current flow, as you can see here from the left hand rule. The current flow, if the current is perpendicular to the magnetic field and the force direction. So if you change the direction of the current, it will change the force direction, or in other words, the spinning direction of the DC motor. So first of all, let's take an example in which we want to control the motor. We connect the motor to the microcontroller immediately. How about this solution? Is it right or wrong? It's wrong, as I say here, but why? Because the microcontroller cannot support the current needed for the motor to spin. So the microcontroller does not have enough current. So the solution was to include the H bridge. Now the H bridge is a circuit based on transistors. As you know, a transistor will need here 0.7 volts is enough to run it. Once it's open, it's like a switch, the current will start flowing from VCC to ground. So here you can see the direction of flowing in this direction. If we switch on the other 2 transistors, the direction of flow will be the other way around. So it depends on the current direction. You can see that the flow is different. Now, how about this connection? What's wrong with this connection? As you can see from this connection, if we connect these 2 transistors, we put them on, the current will start flowing from VCC down to ground immediately, giving us a current equal to infinity, because I is equal to V over R. And what is R? R is almost 0, so this will be equal to infinity. So this for sure is going to damage our microcontroller. So in order to avoid this situation, we build up this circuit. Now this circuit is used to control both direction and speed. Now let's talk first about direction. First of all, we have the enable value, which is this value here, En. Now if En is equal to 0, the output of both AND gates will be 0 and the motor will not start. On the other hand, if En is equal to 1, if En is equal to 1, then the output of these AND gates depends on the input here. So if the input is 0, this means the output of this gate is 0 and this gate is connected to this inverter, this transistor and this transistor. So both of these transistors will be off. Now if the input is equal to 0, then the output here will equal to 1 and here 1, and you can see that this transistor will be on and this transistor will be on, and the current will be flowing in this direction. Okay, the other way around, if the input here was 1, then the output here will be 1 and this one will be 0, and the current will be flowing in the other direction. So earlier I said that this circuit is also used for controlling speed. How do we control speed? In order to control the speed, we need to do what? We need to switch on and off the motor. To switch on and off, we use this port over here. If we switch it off, then the motor will stop spinning. If we give it 1, then the motor will start spinning. So we can use pulse width modulation to do that in order to control the speed of the motor. Now the actual H bridge, it looks something like this. You can see it in the lab. If you remember, we took 3 labs already, and you have already seen the H bridge in the lab and you know how it looks. This is the DC motors connected. Now this is controlling a simple DC motor built on Protos. This is the simulation and this is the code which is used. Okay, this is the code which is used over here. You can see that DDRA means we put port A as output, so we send our output through port A over here, and here you can see the H bridge. Remember, the H bridge needs 2 voltage sources, 12 volts for the motor, 5 volts for the IC. You need to make sure that you have only 1 ground in the circuit. Don't ever design an electrical circuit with more than 1 reference point. Make sure that you have only 1 reference point. Here I have connected only 1 motor. If you want to connect another motor, you have the option over here. If I go back to the H bridge, you can see over here there is 1 output for 1 motor, and here is the output for the second motor. Pulse width modulation is used, and we will be discussing pulse width modulation in more details in task number 3, but here I'm just giving you an introduction how it controls the speed of the DC motor. So if the pulse width modulation is having a duty cycle of 25%, then we are going to get 25 of the output voltage, which is around an average of 3 volts. Now you will say that the motor is on and off, on and off. It will keep shaking. Actually not, because the motor has a moment of inertia اللي هو بالعربي عزم القصور الذاتي, which enables the motor to keep spinning. Okay, which enables the motor to keep spinning even though there is no power on it. And remember, we are doing all of this on high frequency, so there is no time for the motor to slow down in any way. So the next type is the stepper motors. Stepper motors are basically motors which are brushless DC motors. They turn in particular angles, and they have a lot of applications such as 3D printers. Now, working principle the working principle of a DC motor. We have the windings and we have a magnet over here, which is the rotor. And once we energize one of the windings, the DC motor will start spinning. So as you can see here, if this one is energized, then the motor will spin like this. Then we energize these two coils, then the motor will keep spinning. Now, the step angle depends on the stepper motor, depends on the step angle. For usually we have a step angle of 45. 45 is very big, so you can go in step angles very small, up to 0.72 degrees and even maybe less, to have high precision operation. So the minimum angle that a stepper motor will cover within one step or move, which is called the step angle. Now, we have two types of motors, which is a unipolar stepper motor and bipolar stepper motor. The unipolar stepper motor, as you can see, it has one winding, but in the middle we have a common. This common will act as a split in the middle, so this winding will act as two windings. So the current will be flowing in every half in a different direction. In a bipolar stepper motor, you can see we have no common tab in the middle, and the full coil acts as a magnet for the rotor. Now this is good because it will give us higher torque. Now, as per the name, the difference is in the current direction. Here's the difference between the bipolar and the stepper motor. Also, due to the unidirectional arrangement, a unipolar stepper motor do not require control direction of the current. Now, the unipolar stepper motor has less torque compared by the bipolar stepper motor, because the unipolar stepper motor current flows half of the winding. So the current flow is in the half of the winding, and the second half is not energized. Basically, this is the idea of stepper motors. Now, let's go into details on how to control a stepper motor. Now, if we want to do it in a full step, you can see that if we energize these poles over here, the rotor will be halfway. Then here is another halfway, and here we have 4 steps controlling our motor. Now, let's assume that we want to do it half step. So we energize this one, then these two, then this one, then these two, then this one, then these two, then this one, then these two. So we have full step sequence and half step sequence control for the stepper motors. In order to do the full step sequence, the coils A, B, and C should be having these values: 1, 1, 1, 1, 1, 1, and 1, 1 here. Now, for the half step, see, A is 1. Go back here. A is 1, then AB, then B, then BC, then C, then CD, then D, then AD, as you can see over here. Okay, so this is the idea of building it. Now, the ATmega32 can be used to control the to control the stepper motor. You need 4 outputs over here, and these outputs are sent to the ports. Where did we get the values? 9, 8, C, 4, 6, 2, 3, 1. Any idea? 9, 8, 6, 4. Okay, and so on. So this is 4, 5, and this is 2, this is 3. Okay, and so on. So this is the idea of how to control the stepper motor. Now, these are the references. Actually, there is a lot of references online. I advise you to go to electronicwings.com and home to Mechatronics. These 2 websites, they have a lot of information. We still have another type of motors, which is the servo motor. But to understand the servo motor, we need to understand pulse width modulation in full details and how to generate a pulse width modulation, which is discussed in task number 3. Now, in task number 2, you will have to do a report this report, you need to make sure that you do a design for your report. You can upload a video showing your design, because I need to make sure that you wrote your design. Please make sure that you write your name on the code inside the AVR microcontroller. So we need, you can, it's not a must, you can upload a video showing your design. You need to show me the full details of your design and a few runs of your design for that particular task. Hope that this explained everything. If you have any questions, please don't hesitate to ask. Stay home, stay safe, and thank you for listening.